Hello, welcome to Hawk Math. Today we're going to be doing the 2013 MIT Integration Bee qualifying round. Now, in this test, students have 20 minutes to complete these 25 indefinite and definite integrals, but in this video I will not be using the 20-minute time restriction because I want to explain my thought process and explain my answers in a little bit of depth. So starting off with question number 1, I see that we probably want to bring these two log expressions into one term, and the way we can do this, we can write this as the integral of log of x squared minus log of 2x quantity squared, which is the same thing as 4x squared, dx. But then bring those together, we have the integral of log of 1/4 dx. Now, this is just a constant, so we multiply by x and add c. So x, and I'll bring a negative out front, x log 4 plus c, and that's it. Okay, so for question number 2, I see that we have the absolute value, and our bounds go from negative to positive, so I'm going to want to split this up into two integrals. So we have the integral from -1 to 0 on the negative side of e to the negative x dx, because it's negative on that interval. Then we have plus the integral from 0 to 3 of e to the positive x dx. Now, this first part is going to be negative e to the negative x evaluated from -1 to 0. The second part is e to the x evaluated from 0 to 3, which equals, well, when you plug in 0, you're going to get -1. You plug in -1, and you're going to get a plus e to the first. Then when you plug in 3 over here, you're going to get plus e cubed. And you're going to have a minus e to the 0th, which is 1. So which is equal to e cubed plus e minus 2. And we're done with that problem. Now, moving on to question number 3, I see this expression, and I immediately think of the quotient rule. The reason why is because I see on the denominator we have a natural log of x squared, and on the numerator we have the product, the difference of the product of multiple terms whose derivatives are each other. We have the derivative of log is 1 over x, and the derivative of cosine sine is cosine. So, in order to, just to check, I'm going to see what were to happen if we were to take the derivative of sine x over log x, because this looks like it's the same. So, taking the derivative of this, we have log of x times cosine x, minus the derivative of log x, which is 1 over x times sine x, over log squared. And if we notice, that is the same exact expression, so this is in fact the antiderivative, so it's sine of x over ln x plus c, and that's it. Okay, moving on to question 4. I see the expression and I immediately recognize this as the expansion of x minus 1 cubed, because of the 1 through 3 1 with alternating positive and negatives. So it's the integral from 1 to 11 of x minus 1 cubed dx, which is 1/4 times x minus 1 to the 4th, evaluated from 1 to 11. Well, when you plug in 11, you're going to get 10 to the 4th over 4, which is 2,500 minus 0, so that's just 2,500. Moving on to question 5, we see that I see this expression, and I realize we can factor out the 3. So you have the integral from 0 to 2 of root 3, and because that's just constant, we could bring it to the front of the integral if we wanted, times the square root of 4 minus x squared dx. Now, this is just a circle. If we were to graph this on the x and y plane, we see that root 4 minus x squared is the top half of a circle with radius of 2, because we could rearrange the expression to get y squared plus x squared equals 4. And so we want the integral from 0 to 2, which is just this quadrant of the circle. And in order to find this quadrant, well, it's just 1/4 the area of the circle. So the area of the circle is pi r squared, so 4 pi. But then we divide by 4 to get this quadrant, and that's just equal to pi. But remember, we have this root 3, so the answer is just pi times square root of 3. Okay, moving on to question number 6. We have the integral from 0 to 6 of x plus x minus 3 to the 7th plus sine x minus 3. Now, this first part I'm going to evaluate separately from the second part, and you'll see why in a second, because I noticed that this is just 1/2 x squared, evaluated from 0 to 6. Then we have the integral from 0 to 6 of x minus cubed to the 7th plus sine of x minus 3. Now, what I noticed about the second part is that it's symmetric about x minus 3, because 0 is 3 away from 3 and 6 is 3 away from 3. We could do a u substitution here if we wanted by saying u equals x minus 3, and you would actually end up with the integral from -3 to 3 of an odd function, so this whole part is just going to go to 0. Therefore, we're just left with this first part, which is 1/2 times 36, which equals 18, and that's it. Okay, moving on to question 7, we have the integral of sine of x times root 1 plus tangent squared. Well, 1 plus tangent squared is the same thing as secant squared, so we just have sine times secant dx, which is equal to the integral of tangent of x dx. And now the integral of tangent is, it's pretty easy if you do u substitution, u equals cosine x. But you can see this is a negative natural log of cosine x plus c. Moving on to question 8, we have this integral of two polynomial expressions, And one of my options when I see this is to think, since the numerator has a higher exponent than the denominator, is to think of polynomial long division. But before I try that, I'm going to try to factor both of them. I notice that they can actually both be factored by grouping. So we can write the numerator as x cubed times x squared minus 1 plus 1 times x squared minus 1. And the denominator as x cubed times x minus 1 plus 1 times x minus 1. And then we can factor this further to get x cubed plus 1 times x squared minus 1 over x cubed plus 1 times x minus 1. Now we notice that a lot of stuff cancels. This cancels, and this will cancel with the numerator, giving us just an x plus 1 on the numerator. So it's just the integral of x plus 1 dx. And that is pretty easy. It's just 1/2 x squared plus x plus c. And that's it. We do not have to evaluate this. It's an indefinite integral. Moving on to question 9, we have the integral from 0 to 1 of log x. Now, in order to integrate log of x, it's pretty easy. You can just do integration by parts by differentiating log of x and integrating 1. But it's also a pretty easy one to have memorized, so I know it's x, natural log of x minus x, evaluated from 0 to 1. Well, when you plug in 1, you get 0 for the first part minus 1. When you plug in 0, this part's going to be 0. But we have the 0 times the natural log of 0. Well, natural log of 0 is negative infinity. But if you were to take the limit as x goes to 0, this x will go to 0 faster than this natural log of x will go to negative infinity, so this part's going to go to 0 and it won't matter, so our answer is just going to be 1. If you wanted to write that out with formal limit notation, you could. So moving on to question 10, we have the integral of 1 over 1 minus e to the negative x. And in order to rewrite this, I'm going to multiply the numerator and denominator by e to the x. So we have e to the x over e to the x minus 1 dx. And then this is just natural log. I said the numerator is a derivative of the denominator, so therefore it just means it's the natural log of e to the x minus 1 plus c. Moving on to question 11, we have the integral from 0 to pi of sine squared times cosine squared. Now, in order to do this, I know that sine of 2x equals 2 cosine x sine x, and it's much easier to integrate a single trigonometric term. So I'm going to write this as the integral from 0 to pi of 1/4 times sine of 2x squared dx. And the reason why this is the same is you can expand sine of 2x out as 2 sine x cosine x, and you square that, the 4's cancel, and you get sine squared times cosine squared. But we now need to integrate sine squared. In order to do that, I'm going to use the identity that cosine of 2x is equal to 1 minus 2 sine squared x. So we can solve for sine squared x. So sine squared of x is equal to, adding that to the sides, we have 1 minus cosine 2x over 2. Now, we want sine squared of 2x. So we can plug in 2x in this whole equation and get sine squared of 2x is equal to 1 minus cosine 4x over 2. So we can plug this into the integral, getting an integral from 0 to pi of 1/4 times, now we said that we had 1 minus cosine 4x all over 2 dx. Now this is equal to the integral from 0 to pi of 1/8 minus 1/8 cosine of 4x dx. And integrating, we see that we have 1/8 x minus 1/2 sine of 4x evaluated from 0 to pi. Now at pi, we're going to have a 1/8 pi. And then we're going to have a minus sine of 4 pi, which is just 0. And plugging in 0, we would get 0. So our answer is just pi over 8. Now moving on to question number 12, we see that we have the integral from 0 to 441 of pi sine of pi root x over root x dx. And now this is actually a fairly common problem with sine of root x over root x. And so in order to solve this, you can do u substitution, u equals root x. But another hint for that substitution is that you have 441 up in the bounds, and that is 21 squared. So setting u equal to root x seems like it should be a good idea. But I'm going to do pi root x just to get rid of the inside of the sine of pi x. So let's set u equal to pi root x. So du equals pi over 2 root x dx. So now rewriting this integral, we have the integral from, well, when you plug in 0 to here, you're still going to get 0. And you plug in 441, you're going to get 21 pi. Of, now we have pi times sine of u. Now this one, we have dx over root x. So dx over the square root of x is going to be equal to, multiplying, is going to be 2 over pi du. So we have times 2 over pi du. Now the pi's will cancel, and we have the integral of 2 sine u, which is just equal to 2 cosine u. Sorry, negative 2 cosine u, evaluated from 0 to 21 pi. Well, at 21 pi, the cosine is going to be equal to negative 1, so this is going to be equal to 2. And then we're going to have a minus cosine of 0 times negative 2. Cosine of 0 is 1, so that's going to be minus negative 2. So this integral is equal to 4. Moving on to question 13, we have the integral of tangent squared of x dx. And this is pretty simple to integrate. We can rewrite this as secant squared minus 1. And the reason why we want to do this is because secant squared's integral is just tangent. So this just equals tangent of x minus x plus c. Moving on to question 14, we have the integral from 0 to 256 of x minus the floor of x squared. Now, let's think about x minus the floor of x conceptually. If we were to have, let's just say 7.6, then x minus the floor of x would be 7.6 minus 7, which equals 0.6. So x minus the floor of x is just the fractional part of x. And the fractional part of x repeats every whole unit. So, for example, all the numbers from 0 to 1, the fractional parts for x on the interval of 0 to 1 would be the same as the fractional part from 7 to 8. So we can rewrite this really, since all the intervals are the exact same, we could really as only one interval and multiply it by 256, so the 256 intervals. So this is equal to 256 times the integral from 0 to 1 of x minus the absolute value of x on that interval from 0 to 1. Well, not absolute value, the floor of x. And the floor of x from 0 to 1 is just 0. So this just becomes the integral from 0 to 1 of x squared dx. And the integral from 0 to 1 of x squared is 1/3, so we have 256 times 1/3, which equals 256 over 3. Moving on to question 15, we have the integral of e to the 4th root of x dx. Now when I see this problem, it looks a little bit ugly, but I'm just going to test out u equals the 4th root of x and see what happens. So we have u equals the 4th root of x, or u to the 4th equals x, and then 4u cubed du equals dx. So plugging this in, we have the integral of e to the u. Now dx, we said, is 4u cubed du. And that's just an easy integration by parts. So we have 4u cubed, and then taking rid of 12u squared, then 24u, and then 24. And integrating e to the u is just going to be e to the u all the way down. I use tabular. So then this integral is going to be 4u cubed e to the u minus 12u squared e to the u. And then we have plus 24u e to the u minus 24 e to the u. Sorry, I forgot another e to the u down here. And then we have to plug back in our u, though. And when I do this, I'm going to factor out the e to the u. So we have e to the 4th root of x times, well, 4 times u cubed is going to be 4u to the 3/4 minus 12, and then u squared is going to be u to the 1/2. And then we have a plus 24. U is just going to be x to the 1/4. Sorry, these should be x's. And then we have a minus 24, and that's it. And then plus c, and that's our answer. Sorry, it's a little bit messy with the u's instead of x's, but moving on to question 16, we have the integral of cosine x times cotangent x. And I'm going to first rewrite this in terms of sine and cosine. So we have the integral of cosine squared of x over sine of x. Now, this looks a little bit ugly, and I don't think a u substitution on the denominator would work because we have cosine squared on the numerator. So I'm going to try rewriting this in a different way, an equivalent trigonometric expression. And I see that cosine squared we know is equal to 1 minus sine squared. And then we have over sine of x. And let's try expanding this out term by term. So you have 1 over sine of x equals the integral of cosecant x. And then we have minus sine of x. Now, if you know your integrals of trig expressions, then the integral of cosecant should be known as negative natural log of the absolute value of cosecant x plus cotangent x. And then we have the integral of sine is just negative cosine, so you have plus cosine of x plus c, and that's it. Moving on to question 17, we have the integral of 2 log x plus log of x squared dx. Now, again, when I see this, I see something similar to product rule because we have log of x squared here, and if you were to take the derivative of log of x squared, you get 2 times log of x, which is similar to this. So when thinking about expressions that might give this as their derivative, I try to think of something like x times log of x squared. Because if we were to take the derivative of this part, we see that the derivative of x times log of x squared would just give us this term, so maybe the other way around would give us this term. So let's see. So if you take the derivative of log of x squared, you get 2 log x times 1 over x times x, and these cancel, just giving us this term. So this is indeed the antiderivative of this problem. So it's just x natural log of x squared plus c. It's a very useful trick just to try to figure out what the antiderivative is just by looking at the equation. Now moving on to question 18, we have the integral of x cubed over 1 plus x squared dx. And this immediately screams polynomial long division because we can probably simplify this out. So let's divide this out, x cubed and 1 plus x squared. Well, this goes into x, and so then x times this will give you x cubed plus x. Subtracting them, we get negative x, and it doesn't go in again, so that's our remainder. So we have the integral of x minus x over 1 plus x squared dx. And again, these are both the easy to integrate. The second part, if you want to do a u substitution on the denominator, you could, but it's another useful one to have memorized. So this is equal to 1/2 x squared minus 1/2 natural log of 1 plus x squared plus c. Now, moving on to question 19, we have the integral of 1 over x squared minus 2x plus 2 dx. And I noticed that we can probably complete the square on the denominator, and it might be useful to use an arctangent formula. So this is equal to the integral of 1 over x minus 1 squared plus 1 dx. And again, this is just arctangent because we have u squared. If you think about it as a u, we have u squared plus 1. So this will just be arctangent of x minus 1, and then plus c, and that's it. Now, moving on to question 20, we have the integral of sine of x times the natural log of sine of x dx. And in order to attempt this, I don't really know where to begin, so I'm just going to try stuff out. Let's try setting u equals sine x, that's inside the natural log, and see where that takes us. So u equals sine x, then du is going to be equal to cosine of x dx. So rewriting this, we have the integral of u, natural log of u, and then dx is du over cosine x. So we have times du, and I'll just write this as cosine x. But then in terms of sine, we have that cosine of x is root 1 minus u squared, because we know that sine squared plus cosine squared is 1. So this is equal to integral of u ln u over root 1 minus u squared du. Now, when I look at this expression, I see that we might be able to use integration by parts, because it's not terrible to differentiate natural log u, and integrating u over root 1 minus u squared is pretty useful, because the numerator has u while the denominator has a 1 minus u squared in it. So let's try integration by parts. So let's differentiate natural log of u and integrate u over root 1 minus u squared. So differentiating natural log of u, we get 1 over u. And integrating this part, we're going to get root 1 minus u squared with a negative in front. Now, cross multiplying, we have that this is equal to negative natural log of u times the square root of 1 minus u squared. Now we have plus the integral of these multiplied, so root 1 minus u squared over u du. Now, I'm going to try substituting back in the sine x into this expression because it might simplify further. So let's say y equals sine of u. So this will become negative natural log of u, root 1 minus u squared. Remember, this is outside. And then we have plus the integral. Well, sorry, my mistake. This should be u equals sine of y. Now, when we plug this in, we get 1 minus sine squared of y is cosine squared of y, and root cosine squared of y is cosine of y. So this becomes cosine y over, and then u was sine y. And then we have du, which is equal to cosine y dy. So we have times cosine y, and then this is cosine squared on the numerator, dy. Now, if we actually look at this problem, this was the exact answer we had to one of our earlier problems. We had the integral of cosine squared over sine of x dx, and this is the same thing right here. We see that it's equal to this expression. So now all we need to do is just write the final answer. We can plug in what we had, u equals sine x, into this part. So we have 1 minus sine squared is cosine squared, so we have negative cosine of x times the natural log of u, which is sine of x. Okay, now we have plus what we had for this answer over here. Now this answer will give us a minus natural log absolute value of cosecant x plus cotangent x. And then we have plus cosine of x plus c, and that's it. We're done with this problem. It was long, but it was useful because we already had solved part of this expression in an earlier problem. Now let's move on to question 21. So we have the integral of x over 1 minus x to the fourth dx. And I noticed that the denominator of this expression factors, so we probably can do partial fraction decomposition. So this is going to be equal to the integral of a over 1 minus x plus b over 1 plus x plus cx plus d over 1 plus x squared dx. Now, in order to figure out which each one is, we can multiply. Now we can finally plug this all back in, so we have the integral of a over 1 minus x, a was 1/4, over 1 minus x. Then we have plus b, well b was negative 1/4, over 1 plus x. Then we have a plus cx plus d, so that's plus 1/2 x over 1 plus x squared dx. Now what we do is integrate this, so this is not terrible. The first part is just 1/4, negative 1/4 natural log of 1 minus x. Then we have a minus 1/4 natural log of 1 plus x. And then we have a plus 1/2 natural log of 1 plus x squared plus c. Sorry, this should be 1/4, my bad. Because when we multiply this by the 2x, this will become a 1/2. And that looks about right. So we are done with question 21. Okay, moving on to question 22. We have the integral of root 12 minus 3x squared dx. And this looks familiar. And if we look back, we see that it was the same thing as problem number 5, except this time we have no bounds. So in order to solve this, we know it's a circle, and a useful trick to integrate circles is to do trig substitution. So again, I'm going to factor out those root 3 times the integral of root 4 minus x squared dx. Now I'm going to set x equal to sine of u, so then dx is going to be equal to cosine u du. Now we have root 3 times the integral of x equals 2 sine u, and d equals 2 cosine u. Now what this will do is when we square this, we're x squared, we're going to have a 4 sine squared, so this whole expression will become a 2 cosine u. So we're going to have a 2 cosine u, and then dx is equal to 2 cosine u du again, so this will become squared du. And that's all we have. Now in order to solve this, I'm going to square this 2 and bring it out front, so 4 root 3. Now we should have the integral of cosine squared. In order to do this, we can do the same idea as when we integrated sine squared. We know that cosine of 2x is equal to 2 cosine squared of x minus 1. So cosine squared of x is equal to 1 plus 1/2 plus cosine 2x over 2. Now we have 4 root 3 times the integral of, plugging this into here, we have 1/2 plus cosine 2x over 2 dx. And integrating, we see that we have 4 root 3 times 1/2 x plus 1/2 sine of 2x. Sorry, 1/4 sine of 2x. Because when you differentiate that, you're going to get cosine, yep, and then plus c. Now in order to get rid, I'm going to distribute this 4 actually and the root 3. So we're going to have 2 root 3x plus root 3 sine 2x plus c. And that's going to be my final answer. Now moving on to question number 23. We have the integral of secant to the 5th times tangent cubed of x dx. And in order to do this, I noticed that if we were to let u equal to secant, then we would get rid, with the du, another secant and a tangent, and we can rewrite tangent as secant squared minus 1. So when I rewrite this, I'm going to say integral of secant x times tangent of x times secant to the 4th of x times secant squared of x minus 1 dx. So now we can see this part right here, is going to become a tangent squared times tangent gives us tangent cubed, and the secant to the 4th times secant will give us secant to the 5th. So all we need to do is set u equals secant to the 4th, secant of x. And then it becomes pretty natural because the secant x times tangent x times dx will become du. So this will become the integral of u to the 4th times u squared minus 1 du. And this is pretty easy. We can expand it out to get integral of u to the 6th minus u to the 4th du, which equals 1/7 u to the 7th minus 1/5 u to the 5th. Then we need to plug back in, so we have 1/7 secant to the 7th of x. Then we have minus 1/5 secant to the 5th of x plus c, and we're done. Moving on to question number 24. We now have the integral from negative pi over 4 to positive pi over 4 of 1 over 1 minus sine of x dx. Now, in order to do this, I think I'm going to rationalize, because I don't like this 1 minus sine x on the denominator. So I'm going to multiply by 1 plus sine x over 1 plus sine x. And this will give us, when we multiply the denominator, a 1 minus sine squared, which is equal to cosine squared of x. And we can rewrite this expression as integral from negative pi over 4 to pi over 4 of 1 over cosine squared is secant squared. And then we have a sine over cosine squared, which is equal to secant times tangent. Now, both of these are really easy to integrate. This is just tangent, and this is just secant. But before I do that, I'm going to notice that this part of the function is odd. So if we're integrating from negative pi over 4 to positive pi over 4, this is just going to go to 0. So we don't care about that. Now, this first part is even, so we can actually rewrite this as 2 times the integral from 0 to pi over 4 of secant squared of x dx. So this will become tangent of x evaluated from 0 to pi over 4 times 2. So tangent of pi over 4 is going to be 1. So we have 2 times 1, and then tangent of 0 is 0, so minus 0 is just going to be 2. Now, moving on to the last question, we have the integral of 1 over x root x squared minus 2 dx. And now this looks tricky. There isn't an immediate option that jumps out at us, so I'm going to try u substitution. And my first thought of u substitution is to try maybe u equals x squared minus 2. But if you do that, you actually see that it does not pan out. So my second option is actually to let u equal root x squared minus 2. And you'll see why in a second. If we set u equal to root x squared minus 2, then we have du is equal to 2x over 2 root x squared minus 2. These 2's cancel, and we just get that times dx. Now, this is where this substitution comes in handy because this denominator right here is part of the du. So we could rewrite this integral now as 1 over. We have this x was solving for x. We see that u squared plus 2 root equals x. So this x is root u squared plus 2. Then we have this part right here. I'm going to group in with a dx. So we have that dx over root x squared minus 2 is equal to du over x. So, and then remember x was this part again. So du over x, which was this part, we have root u squared plus 2. And we actually see that this becomes really nice because these will combine together to get a du over u squared plus 2. And this again is just the arctangent formula. So this integral just becomes 1 over root 2 times arctangent of u over root 2. But now we need to plug back in what we had for x, so our final answer is arctangent of, now we have u was root x squared minus 2 over root 2, and all over root 2 plus c. And we're done with this problem and the whole test. Okay, now that I finished, I'm going to go through my answers and correct anything if I got it wrong on the answer key, and I'll let you know if I made any mistakes. So I checked all my answers, and they're all correct. However, many of them are actually written differently from what the answer key has. So I'll go through some of those. So in question number 10, the answer key has natural log of absolute value of 1 minus e to the x plus c. And the reason why this doesn't matter is because we have the absolute value bars around it. So we can really distribute it negative in here, and the integral should stay the same. Now, for the next one, which was question number 16, they actually had a very completely different expression, mostly for just this natural log part. This cosine part stayed the same, so ignoring that, we see they had negative natural log cosine of x over 2 plus natural log of sine of x over 2. And you can actually check that these are the same functions, just written in a completely different format. Now, again, on question number 19, they had negative arctangent of 1 minus x, but these are really the same thing. And then on question number 20,
Our answer
was based off the answer of a previous question. Then our answer key, again, their answer had the same answer that we had previously. On 21, they combined these two natural logs into one to get minus 1/4 natural log of 1 plus x squared. And then I think that was it. No, sorry. On question number 25, they had, their answer was negative arctan of root 2 over root x squared minus 2 all over root 2 plus c. And now if you graph these, they actually look different. They're the same function, but the plus c is different. It's just shifted up and down from each other, such that they're the same function, just the plus c makes a difference. So these really are the same answer. I really hope you enjoyed this video. Please like and subscribe if you want to see more like it, and please leave any comments or suggestions down in the description. Thanks for watching.